Questions 21 through 25 on the 2002 Grade 11 Fermat Math Contest. If this expression is equal to 9, then the value of n is. So we've got a big expression here, and it's equal to 9. All right, let's figure out what it is that they are doing. They've given us the first few, so I'll just copy those down, and then we'll try to figure out some more and see if there's something that we can do. So we got 3, 5, 7, 1, 3, 5. So it looks like it's going up by 2 every time, right? Because this is 2n plus 1. So the fourth term would be 2 times 4 plus 1, which is 9. And then the fifth term would be 2 times 5 plus 1, which is 11. And then so on, 13, ... right? ... And it gets all the way to 2n plus 1 and 2n minus 1 for some n. We don't know what n is. That's what we're trying to figure out. And then what about the denominators? Those are going to be 2n minus 1. So this was n equals 1, this was n equals 2, this was n equals 3, and so on. N equals 4, n equals 5, n equals 6. So let's figure out the denominators. 1, 3, 5. Well, I have a strong suspicion of what it is, but let's work with this. 2n minus 1. So if n is 4, it would be 7. If n is 5, it would be 9. N is 6, it would be 11, and so on. So I think you have an idea of how this goes. It would just be, the numerators would be 3, 5, 7, 9, 11, 13, 15, 17, 19, and so on. And the denominators 1, 3, 5, 7, 9, 11, 13, 15, 17, and so on. Now I hope you can see that since this is multiplication, we can cancel. This cancels with that cancels with that. 7's cancel, 9's cancel, 11's cancel, and so on. Everything will cancel all the way to the very end. The only thing that remains is the 1 and the 2n plus 1. So this whole thing simplifies to just 2n plus 1 over 1. That's it. Okay? So then we square both sides, get rid of the radical, the root, and that would be 2n plus 1 is equal to 81. 2n therefore is 80, and n is equal to 80 divided by 2, which is 40. And that's it. 21 will be C. The function f at x has the property that f at x plus y is equal to f at x plus f at y plus 2xy for all positive integers x and y. If f at 1 is equal to 4, then the numerical value of f at 8 is. So f at x plus y is equal to f at x plus f at y plus 2xy, like that. And that's pretty much what we have to work with. And they've given you one clue. F at 1 is equal to 4. And that's all they give you. So that's the only thing we have. That's the only thing we can work with. So f at 1 is equal to 4. So if I put that in there, in that place, and also f at 1 in this place, that means that I've made my x equal to 1, and I've made my y also equal to 1. So this becomes 2 times x, which is 1, and y, which is 1. So that takes care of that side. On the other side, the left side, f at x plus y. But remember, I made my x equal to 1 and my y equal to 1. So with the only piece of information that they give us, this is what I create. So that means f at 2 is equal to, well, what is f at 1? It's 4, the numerical value. F at 1 again is 4. And then 2 times 1 is just 2. So this becomes 10. So f at 2 is equal to 10. Now they want us to find f at 8, so we obviously have to keep going here in the exact same way, using this as our equation. So here we go. F at 2 is 10. So in this position, I'm going to put f at 2 now. And same thing with f at y. And therefore what I've done is I've made x equal to 2 and y equal to 2. So this now becomes 2 times 2 times 2, like that. And then therefore f at x plus y is 2 plus 2. So this now becomes f at 4. F at 2, the numerical value is 10 plus 10 plus 2 times 2 times 2, which is 8. So this is 28. So f at 4 is 28. And now we get to the part where we can figure out f at 8, which is what they want us to figure out. I think we can do it. F at 4 is what I'm going to substitute here. So we got f at 4, and then again f at 4 for this guy right here. And then what I've essentially done is let x equal 4 and y equal 4. So that means you have 2 times x, which is 4, times y, which is 4. And then the left side becomes f at x plus y, which is 4 plus 4. And therefore now we've got f at 8. F at 4, the numerical value is 28. Another 28 there. And then 2 times 4 times 4 is 32. And therefore 28 plus 32 is 56 plus 32, which would be an 88. F at 8. So 88 is the answer, and therefore 22, the answer is C. The integers from 1 to 9 are listed on a blackboard. If an additional m8s and k9s are added to the list, the average of all the numbers in the list is 7.3. The value of k plus m is. So you've got a blackboard and they've written the numbers 1 through 9 on it. And then in addition, they put a whole bunch of 8s. 8, 8, 8, 8. We don't know how many 8s. Dot, dot, dot. Dot, dot, dot. Whole bunch of 8s. But the only thing they tell us is that there's m of them. And then they also put a whole bunch of 9s. 9, 9, 9, 9, dot, dot, dot. And we don't know how many, but they tell you there's k of them. And then they take the average of all these numbers. So how do you take the average of a bunch of numbers? You add them, of course. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. And then we're going to add a whole bunch of 8s. So we don't know how many, but we know the sum will be 8m. Correct? There's m 8s. So the sum will be 8 plus 8 plus 8, 8m times, and that therefore that is the sum. And very similarly, the sum of the 9s is 9k. Okay? And then, of course, you divide by the number, the total number of numbers. And that's 9 of these guys. M 8s and K 9s. And they tell you that average is 7.3. All right? So that's basically the mathematical equation that we have to figure out. We eventually have to figure out k plus m. So either we will get to a point where k plus m equals something, or we will get to an equation, and through inspection we will have to figure out individually the values of k and m. All right, let's proceed with this. This sum here is 45 plus 8m plus 9k over 9 plus m plus k, and that is 7.3. All right, let's move this up. Now, at this point, where do we proceed, right? Do we cross multiply and all that? And there's a lot of ways to proceed at this point, and it's entirely dependent on your level of comfort. Some people factor, and some people will, cross multiply. So I'm not going to show you what is, the best way. What I mean by that is there's many ways, and I'm just going to show you what I'm comfortable with. It's not necessarily the best way. what I'm going to do simply is just cross multiply. No magic, no tricks, nothing. So if I cross multiply, I'll get this 7.39, 7.3m, and 7.3k, like that. All right, so here we go. 7.3 times 9 will give you 65.7, and then I'll bring the 45 over, and then I'll put all the m's on one side, 8m minus 7.3m, and then we've got 9k minus 7.3k. So that's basically what I'm going to do. 20.7 for the number section, this is 0.7m, and this is 1.7k. Okay, now at this point, unfortunately, we only have one equation. If we had two, that'd be a great piece of cake. But we don't, we only have one. So when you only have one, you have to basically plug in numbers. Now the good news is that m and k are integers, right? Because there was m8s, there was k9s. So m and k obviously are integers. So make yourself a table and start plugging away. And the hope is that you don't have to do this forever, that the integer solutions will come quickly, because you have limited time on a math contest, as you all know. So if k equals 1, put in k equals 1 into our equation here, and you'll get 27.1 for m. So no good, right? K and m have to both be integers. K equals 2, you get 24.7 approximately. K equals 3, you get 22.3. K equals 4, 19.8. K equals 5, 17.4. And at this point you're thinking, oh boy, how long do I have to keep going here? K equals 6, you get 15. There you go. These are your integer solutions. So if you go back to the question, 6 and 15 were k and m. So k was 6 and m is 15. So there was 15 of these 8s and 6 of these 9s. And they want you to figure out k plus m. K plus m is, of course, 21. So number 23, the answer is B. This question I will solve in about 10 seconds, but the number might be a little different. Don't get confused by that. It's the exact same question. A student has two open-topped cylindrical containers. The walls of the two containers are thin enough so that their width can be ignored. The larger container has a height of 20 centimeters and a radius of 6 centimeters and contains water to a depth of 17 centimeters. The smaller container has a height of 18 centimeters, a radius of 5 centimeters, and is empty. The student slowly lowers the smaller container into the larger container as shown in the cross-section of the cylinders in Figure 1. As the smaller container is lowered, the water first overflows over the larger container, Figure 2, and then eventually pours into the smaller container. When the smaller container is resting on the bottom of the larger container, the depth of the water in the smaller container will be closest to. So, the first thing I want to do is figure out the volume of the water in the container before anything happens. Okay? Before any smaller container is lowered and all of that. So, that's our first step. So how do we figure out the volume of a cylinder? Pi r squared times height. All right? So in our case, we have pi. What is the radius of this big guy? So because it's the big one, I'm going to use big R and big H. The radius of the larger container is 6 and the height is 20. But be careful. The radius is 6, that's fine. 6 squared. But in our example, the water doesn't go up all the way to 20. It only goes up to 17, and you can clearly see that in the diagram. So we have to use 17 for the height of the water. So therefore, this becomes pi times 36 times 17, which is equal to 612 pi. So this represents the initial amount of water. Now, step number 2 in this question is to figure out what happens when this small container right here that is empty is lowered into the bigger one. Now, notice initially nothing's happening. It only starts to overflow once the small container touches the water and pushes it to the top. Up until that point, nothing overflows. It only overflows once the water is all the way at the top. All right, very important to understand that. So second thing I'm going to do is figure out how much water is remaining once this container is lowered into the bigger one. So this represents the scenario of when the smaller container, which I have drawn in green, is lowered all the way into the big container, which I have drawn in black. And the blue bar at the top represents the level of the water. That water that is in there is what we need to figure out. That is how much is remaining, because all the rest of the water has flown right out. Okay? So how do we figure out the volume of the water that is remaining in this figure now? Well, we take pi big R squared times height, the whole cylinder, and then we subtract from it, obviously, the empty small cylinder, which is going to be pi small r squared small h, like that. Okay? And this is VR, volume remaining, volume of water remaining. So let's see. Pi, radius of the big cylinder was 6. They tell you that in the question. The height, the full height of the big cylinder is 20. And then pi small r, the container that is smaller has a radius of 5. And the height of the small container is 18. So this becomes pi times 36 times 20 minus pi times 25 times 18, which is 720 pi minus 450 pi. And this is 270 pi. So this is how much water is remaining. And now the next thing I'm going to figure out is how much flowed out. Well, that shouldn't be too hard. Initially, you had 612 pi of water, and 270 is remaining. So if x represents how much flowed out, x can be calculated pretty straightforward manner, in a straightforward manner. It's just 612 minus 270, and therefore x is 342. So this is the amount that flowed out. All right? Now, I want you to figure out the volume of the small cylinder, because that's pretty important. Volume of the small cylinder, pi small r squared times small height. If you remember, the radius was 5, the height was 18. So this is 450 pi. Now I want you to compare the volume of the small cylinder to the amount that flowed out. I forgot a pi there. Compare 342 pi to 450 pi. The amount that flowed out is less than the volume of the small cylinder. Why? If you put that small cylinder in, wouldn't the amount that flows out be equal to the small cylinder? why is the amount less? And that is a very important part of this question that is crucial. The reason is because look what happens when you first put the small cylinder into the big one. Initially, the water level rises to here, right? But nothing is flowing out until you get the water all the way to the top. And the reason is because the water level initially was at 17. It was not at 20. If the water level was initially at 20, then yes, the amount that flows out would be equal to the volume of the cylinder. But the initial height of the water is not 20, it's 17. And that is a crucial part of this question that unfortunately can get you the wrong answer or get you an answer that's not even close to the answer choices. All right, so we are basically at our final step, step number 5. And I need to draw a diagram. All right, so before I get to the diagram, I just want to emphasize that point that the amount that flowed out, 342 pi, is less than the volume of the small cylinder, and I explained why. All right, now we get to the final step. So the final step is when the small cylinder that I've drawn in green is at the very bottom. It's sitting at the very bottom, and all the water is now settled. The amount that flowed out is gone, and the water level is now at the very top to match the height of the small cylinder, and a segment of the water has flowed into the small cylinder. All right, so now we have to figure out this value right here, right there, the amount of water, the height of the water inside the small cylinder. I'll remind you, look at the question again. The depth of the water in the small container, that is what they want. All right, so I've denoted that with this orange line, and I'll call it y. I'll give it an actual value. We'll call it y. All right, so now this is how we do this. Our remaining water is 270. That's how much water is remaining, okay? So 270 is a very important number for us. And how do we figure out that? Well, we have to figure out the area of this blue shaded region. So it's the whole cylinder. So pi r squared height minus the small cylinder, pi r squared height. But our height is not going to be 18, which is the height of the small cylinder. Our height is only going to be from here to here, because that's the part that's empty, and that's what we have to subtract. So from there to there, what is that? Well, we know the height of the total cylinder, the small one, is 18, right? And this is y. So this segment here has to be 18 minus y. Okay? Like that. So let's start plugging in our values. Pi r of the big cylinder was 6. So we got 6 squared. And the height, we are only interested in this height right here. And that is 18. Why? Because that's the height of the small cylinder. So be careful about the numbers that you're putting in. Pi r squared of the small cylinder, and that radius was 5. And then height, we're subtracting the empty part. So that is going to be 18 minus y. Like that. All right, so this is going to give us our value for y. The pi's cancel, so that just leaves you with 270. And we get 36 times 18, which is 648. And this will give you 25 times 18 and plus 25y, like that. So we got 270 is equal to 648 minus 450 plus 25y. And this becomes 648 minus 450, which is 198, 270 plus 25y. And then 198, put that over on the other side, and that's going to give you 72 is 25y. And then finally y is going to be 72 divided by 25, which is 2.88. And there you go. That is what they want you to figure out. The height of the water in the small cylinder when the cylinder is all the way at the bottom. So 2.88, let's see what we get. Number 25, 2.88 is choice D. The lengths of all 6 edges of a tetrahedron are integers. The lengths of 5 of the edges are 14, 20, 40, 52, and 70. The number of possible lengths for the 6th edge is. So here you have some tetrahedrons, and we're looking at it from the top, a bird's eye view. And we are told that our sides are 14, 20, 40, 52, and 70, and they want you to figure out the 6th sides. The 6th edge, the length of that 6th edge. So the first thing I want to mention is that if you have, let's say, a triangle, any triangle like that, there's a fundamental rule that if this is A and this is B and this is C, where C is the longest side length, A plus B has got to be greater than C. Okay? So that's something you probably already know, but it's going to be used repeatedly in this question. So now, let's start with our first tetrahedron and figure out how to place these sides. 14, 20, 40, 52, 70. Okay, well, let's see how I can do this. I'm going to let this side be 70. All right? I don't know, but let's see if it works. And then I'll choose 40 here and 52 here. Now, what's remaining? What sides are remaining? The 14 side and the 20 side. Okay? Now, can I make 14 and 20 go anywhere else? Right? That's my dilemma here. Well, first, before I get too ahead of myself, let's look at the triangle right here that I've labeled. Is this legitimate? And we're going to look at that rule. A plus B is greater than C. Well, 40 plus 52 is greater than 70. 52 plus 70 is greater than 40. And 40 plus 70 is greater than 52. So that's perfectly fine. But is it though? That triangle is okay, but I still have to put in these guys. Otherwise, this triangle is of no use to me. By itself, it's fine, but let's see what happens when I put in 14 and 20. All right, let's just put 14 here, 20 here, and see what happens, where 20 is the length of that side, and 14 obviously is the length of that side. Is 14 plus 20 greater than 40? 14 plus 20 is 34. Well, that can't work. I can't have a triangle like that. And therefore, this is no good. So put an X there. I can't make these triangles work with these sides, with this arrangement. So the only arrangement must be that that's 70, that's fine. But I've got to make this 20 and this 52. Okay? That's the only way. Now let's verify that. How about just this triangle right here? Does it match our rules? This fundamental rule up here. Well, 20 plus 52 is indeed greater than 70. 52 plus 70 is indeed greater than 20. And 20 plus 70 is greater than 52. So that is fine. Now, what do we have left? We have a 14 left and we have a 40 left. Correct? Now, we have to figure out how to place those. So let's use another set, fresh right here, 70, 20, and 52. And we've got to place 14 and 40. All right, I'll place 14 here and 40 here, where 40 is that length and 14 is that length. Okay, does this work? 14 plus 40 is greater than 20. Okay, good. 40 plus 20 is greater than 14. 14 plus 20 is 34. It's not greater than 14. 14 plus 20, is it greater than 40? No. So unfortunately, this scenario, again, no good. All right, start again. This one we know is legitimate, so we've got to somehow place 14 and 40. This way of doing it doesn't work. So let's try another way. Let's try 14 here and 40 here. Let's see if that works. So looking at this triangle right here, 14 plus 40, is that greater than 52? Yes, it's 54. 40 plus 52 is definitely greater than 14. And finally, 52 plus 14 is greater than 40. So that works. This is correct. So that means x, that sixth side, the sixth edge that they want us to figure out, must be here, where I placed it. All right? Now, we actually have two scenarios. This is definitely one scenario, but there's another scenario. This is the first scenario, x, 14, 40, 52, 20, and 70. But there's another one. You're just reversing the 40 and the 14, like that. So the 40 would go here, and the 14 would go there. That would still make that triangle completely legitimate with regard to our fundamental rule, that the sum of the two sides have to be greater than the third side. I'll even write that rule again, that A plus B has to be greater than C. All right, using these two triangles, we will now proceed to figure out what x can be. What values can we have for x? And are they integers? Yes, all of them are integers. Okay, here we go. So, in this triangle, we just keep using our rule. We're going to first concentrate, of course, on the x, and that's really all we need to concentrate on. This triangle right here, right there. So in that triangle, the first thing is 14 plus x has to be greater than 20. All right, that's our first rule. 14 plus x has to be greater than 20. Another rule, of course, is that if you look at the entire triangle like that, we can also get an additional relationship with x, 40, and 70. So that's also going to help us out quite a bit. And I'm going to do that as well, because this one itself won't give me a boundary. I'll see if it does, but I doubt it. X plus 14 is greater than 20. So that means x is greater than 6. All right, x is greater than 6. Whoop. That means it could be anything, right? So we need a boundary. Now, staying with the same side for now, there's another relationship, right? And that is that 14 plus 20 have to be greater than x. This 14 and 20 have to be greater than x. So that means that x is less than 34. So with a little bit of patience, you can see that working with one triangle does indeed give you a boundary. So that's great. We've got x is greater than 6, but less than 34. Okay? Now, before we move on, I hinted at it just briefly, but I'm going to show you again that we also have to consider that triangle right there. Sometimes, you get the right kind of path in a question and you just do it and move on, but pause and see if there's additional ways of making this answer a little more correct than what we think it is. Now let's look at the full triangle, this big one right here. In that triangle, you can see that x plus 40 must be greater than 70, correct? And that 40 plus 70 must be greater than x, like that. So from the first one here, that means that x is greater than 30. And from the second one, we just get x is less than 110. Now we have to combine these two. So that means x is less than 110 and greater than 30. Now what we have to do is combine these two guys. Now how do we do that? Well, if you have a number line, let's say, simplest way to do it I think is a number line, and we've got x, we've got 110 here, we've got 34 here, 30 here, and 6 here. From our first one, x is between 6 and 34, so it's somewhere here. From our next one, x is between 110 and 30. So the common is what we look at. What's common? It's right here. Do you notice how that was common to both? So what's common? The solution of this, if you combine these and these, is x is between 30 and 34. All right? Notice less than, not equal to. So what are our integer solutions? I'll write them in here. X is going to be 31, 32, and 33. Okay, so I hope you understand how that happened. We're going to do the exact same thing on this triangle right here. So hopefully, since I've already done it once, the second time, you can probably do it on your own. So here we go. All right, so first let's concentrate on this triangle right here and see what we get. So from that triangle, we know that x plus 20 has got to be greater than 40. Same rule. And therefore, another condition of that triangle is that 20 plus 40 has to be greater than x. All right, so from the first one, this basically means that x is greater than 20, like that. And from this one, we'll get that x is less than 60. So if you combine these two, x, the boundaries are greater than 20 and less than 60. Okay, so that's our first. Now we have to look at the big one, the full triangle. From that one, you'll see that x plus 14 has to be greater than 70. And another way of looking at it is that 70 plus 14 has to be greater than x. From the first one, you'll get x is greater than 56. And from the second one, you'll get that x is less than 84. So combining these two, x is basically greater than 56, but less than 84. So these are our two solutions, and we have to combine them now. So very similarly, I put them on a number line, and let's start labeling our number line. Our upper limit is 84, our lower limit is 20, and then we've got the numbers 56 and 60. All right, so let's look at this. From the first one, x is between 60 and 20, so it's this orange zone. From the next one, we've got a scenario that x is between 84 and 56. So 84 and 56, like that. So the common zone to both of these is right here. X is between 56 and 60. So that means that x is equal to 57, 58, and 59. Notice it's less than, not less than or equal to. So there you go. We've got more solutions. 57, 58, 59, and we had up here 31, 32, 33. So how many possible x's did we find? Well, down here we found 1, 2, 3. And up there we found another 3. So 4, 5, 6. 6 possible solutions for x that make the tetrahedron have 6 edges that are all integers. So number 25, the answer is 6, which would be choice E.